Yeah, I've been in the applied ML space for a while. Today we'll talk about recommender systems, yes, but we'll also talk about, generally speaking, we'll talk about how applying machine learning is a direct way to grow your top line objective of the business. I won't have time today, but that is essentially the secret of high frequency trading. How in the past people had models for something slightly tangential, but when I spent about 15 years in high frequency, what we did in the very beginning is that we directly started optimizing the top line objective of the company, and that applied ML now, same in ads, same in homepage click-through rate, in other industries has worked very well. Today's talk is about recommender system and creator economy, but also about applied ML. And if you guys have questions later on, I'd love to contribute as much as I can in that. But going back to my introduction, I 15 years after dropping up from PhD, where I was sort of researching some of those aspects. I was the youngest partner in Tower Research Capital. I built a system that I was given seed capital about $10,000, and I built a system that I think made about 700 million when I was there. Then onwards, I started my own high frequency trading business, and then a fintech business. And in Google, I led personalization for Google Assistant and the ML side of it, and the podcast recommendations from scratch. It was a project we started. I'm very fortunate to have got a project at Google that you kind of start from scratch. Not much of you don't get that many chances to do that nowadays. We built that, and then more recently I'm in DevRev, where it's stealth mode, so I won't say much, but we do something in the B2B SaaS. We're building something for developers. Okay, so there'll be terms that might be new to you. Please sort of keep asking questions, and Weber will moderate and relay it at appropriate times. But yeah, I want this to be interactive. Okay, some ground definitions. A recommendation is, as opposed to search, a recommendation is content that is shown to you without your having explicitly given an intent. And search is where you specify an intent, and we are trying to interpret that intent, serve something for that intent. In recommendations can be unpersonalized or personalized. For instance, on the left, you see a person going to this home. This is the app I built recommendations for. But you go to the homepage on the left is the same for everyone. There's no difference. Like, this is when the person has signed in, and there's no data about the person. Hence, the experience is the same for every new user. And now this user listens to a podcast. So you can see the one in the right image at the bottom. It's TikTok and Beyond, which I think is appropriate for this presentation. It's a very good podcast, by the way. I recommend you guys listen to it. It's by Eugene Wei. And so once the user has listened to this podcast, you can see the homepage changing. So Masters of Scale with Reid Hoffman is roughly on the same topic, same genre. Microsoft and Discord. Again, you can see slight difference, but it's somewhat related. So this experience is called personalized recommendation. Now, coming back to what I said about using machine learning for the objectives of the platform. At a high level, this is one view. This is not the only view of growth, but you have users and you have to do user acquisition and then activation, retention. So user acquisition means getting people to know that you exist. Activation is sort of helping them figure out what can you do, what is the utility of this platform, this app, and finding the first aha moment, as they call it. And then retention is about doing a good job so that they keep coming back. Recommendation is today the primary lever of growth for activation and retention for the YouTube, Spotify's, TikToks of the world. There is nothing that comes close. Yes, there's product work. Yes, there are other aspects to it. But the single biggest growth lever is recommendation. Recommendation is about finding what you're looking for, connecting you to the content that you're looking for on the platform. Examples: higher click-through rate. If you make a model which delivers higher click-through rate, you can say you can lead to greater user activation. If you keep doing that and yet also introduce content that the user comes back for. I'll give examples. Let's say you have on Amazon Prime, let's say you have 2 videos to recommend to the user. One is say Gemini Man, which is a movie, and the other is the first video of a series of 7 seasons. Then the second recommendation will lead the user to come back for more. So of that recommendation is higher. These are things that will help you in higher retention. User satisfaction is an important thing, and I'll touch upon it later. But when you're developing when you think about the metrics for your recommender system, especially when you're A/B testing between different implementations of the recommender system, you'll want to not just optimize on engagement, but you'll want to optimize on satisfaction as measured by actually asking the user. I'll not to spill the beans, but they are not the same thing. User satisfaction. The difference is clickbaity content. Clickbaity content has higher click-through rate, not satisfaction. I guess I was sort of talking about the slide. And one other metric is responsibility. So we talked about engagement, click-through rate, page level click-through rate. Let's say it's a podcast or music ecosystem, the average time listened by the user per month. And satisfaction is you ask a sample of your users, ask them what's 1 to 5 rating of what you just listened to. And the responsibility is that was it offensive? Was it inappropriate? So these metrics and more you need to look at while making launch decisions. Okay, you're making a context switch sort of. Before I do that, I want you to understand. I want you to understand that starting with the objectives, we are working our way backwards towards the model. If you recall what Weber posted about the event, first we'll talk about the state of the art in recommender systems. Then we will talk about its problems in terms of objectives, and then we'll try to change the architecture to perform better, to not have those problems. But first, so this is the traditional collaborative filtering approach to personalized recommendations. The data you have, the data you're able to log is a lot of instances of a user, let's say, listening to a certain item, another user, another item. You just have this list of these events. From this, you have to learn something so that tomorrow when users come, you're able to recommend the appropriate, the best job you can do in recommendation. Okay, so any questions on the log data? Okay, I kind of should see the chat window. Yeah, please feel free to ask questions.
No questions yet.
Okay, sounds good.
Folks, just put in the questions. If you have any issues in the way, any questions, just put it there and we'll,
Sounds good. I'll come to the cold start problem, thanks. And we recommend generating better log data. Okay. Initial set of data. Okay. Sounds good. Cool. But as far as the log data is concerned, I believe, there are no questions that the log, what we are logging from real interactions is that at a certain time, certain user listened to a certain event, a certain item. Now, the collaborative filtering approach, what it does is it tries to learn an embedding for each user in each item so that for the items that the user has learned, their embeddings should be very close by, very similar. An embedding is a vector, but for our purposes, let's assume an embedding is the categories of the items embedding are the categories of the item, like whether it's a sports item or a news item or comedy, etc. And then what we are trying to learn with this collaborative filtering approach is slowly we are trying to learn embeddings of users and items so that user one and item one, they should have close by embeddings, because I've seen in the data user one has listened to item one. Similarly, user two and item two should have close by embeddings. Okay. I'll come to questions after this. I don't see any related to this slide. So for instance, yeah.
I'll take them and bring them in later.
Sounds good. Okay. So by the way, the method we are talking about is a seminal method. This was introduced in 2007 by Yehuda Koren, whom I had the pleasure of working with at Google, and Koren and Bell in the Netflix Prize. And then there were a lot of improvements being made. Back then, it was using matrix factorization, and then people used weighted alternating least squares, WALS, and then people used stochastic gradient descent, so general neural network sort of machinery for this problem. To give you an example, just to visualize, it should be very clear what is actually happening under the hood. So imagine all of these different colors are different categories. Again, let's say we're talking about podcasts, so something can have, an item can have, let's say sports, comedy, news, and sci-fi, or news and not sci-fi, but I don't know, let's say technology. These are four genres. Now the thing is, we are not trying to categorize with expert human labelers. We're trying to understand, on the right, we are trying to understand what categories does an item belong to, and being on the left, we are trying to understand what categories the user likes. We're trying to understand these both things purely from data. Exactly. Thank you, Vishnu. The question is, could you please clarify the meaning of embedding once again? An embedding is a score per category. So a user embedding is how much the user likes a certain category. So hence, you'll have a score as many categories there are. Later on, we'll stop using the word category, but let's pretend right now that's all we're doing. There are these magical categories, let's say in this case 4, these magical categories that are perfect for our system. We don't know them, but we know that there are these things. And we just have to figure out how much each user likes content from these categories. Similarly, we need to know for each item, what is its belonging to each category. Is this a sports item? Is this a comedy item, etc.? Okay. Okay. So what we have to learn is we have to learn categories from data, and that's what we learn by stochastic gradient descent. Initially, we start with random. The top row is just randomly assigned. So we take all our users and all our items and just randomly assign numbers as their categories. But then we take the log data and we see that, oh, this user listened to this item. Hence, we need these to be close by. The best way of making close by is to make them equal, but that would account for a learning rate of 1. In practice, the learning rate is much smaller than 1, like 1 to 10 to the minus 5 or something. But if you had a learning rate of 1 and you had a single example for this user and item, what you would learn is that their embeddings are average of the inputs. So 10 plus 0 by 2 is 5. 0 plus 8 by 2 is 4. Minus 10 plus minus 2 by 2 is minus 6. Similarly. So what happens is you initially start with random embeddings, and you slowly look at every single instance of users and items, and you run your stochastic gradient descent, and slowly at the end, what you have is a user's embeddings are very close to the embeddings of the items they have listened to. And that is your output of that. This is your training step. At the end, you have this output, and now you have to store these user embeddings in a database and the item embeddings in a vector database. And from there, you have to, this is what you need for serving your recommendations. This is what is collaborative filtering. Okay, please let me know if you have any questions on this. I'll move on.
Any questions, just type in, folks.
Okay, so what I described was, it was the state of the art about 7-8 years ago. What was deficient in that model? What was deficient in that model is that we were not seeing anything about that item. We were not seeing who is the creator of that item, what is the when was it published, how is it new, etc. We were not seeing any item features. We were not seeing any user features. Where is the user located? What language do they convert in, etc. We are not seeing any. We were not seeing the user history directly. It's a little technical why we were not seeing, but essentially when we train this data, we train it in parallel, which means that the user embedding does not get to look at the history while being trained. This is what was changed here. Now, and this is the state of the art in personalized recommendations today. If you go to Facebook, Google, Amazon, any top of the line recommender system, the approach that is used is a 2-tower model where these arrows are actually neural networks. On the user side, you have a neural network which looks at the user history, which means that in our case, what items the user has listened to in the past, and it learns to convert it into an embedding. On the right side, for each item, you have the categories as specified by the publisher, and also you have the name of the publisher, or the ID of the publisher. This is what will help you see that a Lady Gaga video is going to be much more popular than my video or something. Okay, there's a question. Hang on. The first question is, how are initial item embeddings random? They would be assigned by human labeling, just right like which genre they're coming. Very good question. So Smriti is asking that, in this previous slide, why did we start with random embeddings? Why didn't we start with another approach would have been, we have expert labelers who take an item and assign them categories, like category scores, and we start with that. Firstly, that's hard to scale if you have billions of videos coming in to, let's say, YouTube. That is one approach, but costly approach. This model, and there are many research papers, this model actually comes up with better categories than the human label categories. So for instance, you and I would talk about categories like sports, comedy, news, etc. But the dimensions that this model comes up with Oracle given categories, so to speak, are not sports, news, sci-fi. There's something latent, there's something hidden, there's something that we don't necessarily translate to English words. And these are better. There are models which show these are better categories than human labeled categories. Okay. Next question is how to approach, I guess, recommendation if the content is dynamic, like new content. Yep, that's also called the cold start problem. What we described here was, it works very well in the sense that if I have an item for which I have a lot of data, I'll learn an embedding. But if I have an item that is completely new, I have no past interaction of it. And like we said, we'll start with the random embedding, which means like tomorrow, this random vector will not be close to any user's embedding, and we won't recommend it to anyone. So very good question, Ankit, that in this approach for new content, we will not have a good solution. We'll talk about how to explain that. Just a question for later on. Since two-tower models takes into account item, learning from this to recommend products from a different category, like cross-category recommendation, for example. If you like a particular t-shirt, you may like a bracelet to go along with it. I think you're mixing two things. If you buy a t-shirt and then what you buy next, that is still same. Yes, I use the word category, but essentially in the domain of e-commerce, it is still the same domain, the same relationship of user buying something. And you can learn that causality in this model, because you can learn that if the user history on the left has a t-shirt, then often the user ends up buying a bracelet. Or there's a traditional example of if a user buys a laptop, then they buy a laptop bag, and not the other way around. If a user buys a laptop bag, not all the time do they buy a laptop after that. However, I think that there's a deeper question that if I know which news articles a user reads, does that translate to which music they will listen to? Or does that translate to, I don't know, what they will select on Airbnb? Or really different domains. And there is research on that. What the things to follow up would be sort of graph neural networks. I think that's an effort towards having multiple types of nodes in the same graph. Okay, sounds good. So another question: how would a new creator find audience in the two-tower model? Yep, good question. Creator side we haven't directly talked about. We'll come to that. But actually, you see the little publisher on the right. It is a very important signal to get high quality recommendation. Why? What else do you have on this item? You have category and you have publisher and you have this latent embedding. Let me explain what latent embedding does. Suppose you have 3 videos from Lady Gaga. One has 1 million views, second one has 100 million views, third has 1 million views. There's something different about the second video. If all you had was the publisher, if all you had on the right side was that this is a Lady Gaga video, then you would not have enough information to differentiate between these 3. So the something different is what is captured by the latent embedding. It learns what is different about each video. The problem is that it will have this cold start problem, as in for a new video, you will not know what is different. Okay, so nowadays we are trying really hard in state-of-the-art recommender systems to not have a latent embedding, to learn as much as possible from the publisher, from the category, from the title, description, acoustic signals, from images, everything about the item, and not a latent embedding. However, publisher is an important signal. Like I mentioned, if there's a Lady Gaga video and my video, we have seen that a certain publisher does much better, and Not having that signal seriously reduces the click-through rate of the model that you built. And the question, I believe, the question was, how would a new creator find audience? So for a new creator, we will not have any information about that creator. And so we'll come to that. Like essentially, in the model that I said, the new creator will get less views than a Lady Gaga video, or a publisher for whom we already know that they're successful on the platform. That is just because this publisher is an input to this model, and we have while training, we'll already learn the goodness of each publisher. Okay. I know we are thinking of it as if it's a problem, given the context of the talk, but it's actually very natural, right? If you, I don't know, if a Disney movie comes up, you expect it to do well. So it's a strong signal that one should have in your model. Okay. 2 questions. How to prioritize some embeddings, like we need specific embedding contributes more in the recommendation, how to handle it, how to use business rules like filter those items containing inappropriate content. Yeah, so we're not talking about filtering. Usually in a recommender system, what happens is you have retrieval, which is a step which looks at all your content. Let's say you have billions of items you can recommend from. The first step looks at billions of items, comes up with a small set of 100 items, 100 or 200, some small number like that. And that small set of items, you have a more powerful neural network ranker, a neural network or decision tree ranker that ranks them, and then you filter the ones for inappropriate content. In some cases, your neural network ranker also has a filtration head, which means that you can have you can make it as strong and sophisticated as you want. But filtering is a separate step. It's not a part of recommendation. We can always think of it. Okay. So now, so where we are is that this is the state of the art. The 2-tower models are pervasive. They're very powerful. And to give you some sort of numbers without naming a company, but one of the companies I work with, you can guess which one. We started with under 1% in click-through rate, and after all our efforts of retrieval, ranking, and clustering and training for different user cohorts, etc., the click-through rate increased as much as 8.1%. So about 9 times from where we started. So it's a very, very powerful model. The numbers are much higher for like video recommendation places like YouTube, like page level click-through rates and stuff. Very high. So it's a very powerful model. It's used everywhere. There are nice tutorials of it on. If you want to see Google developer, search Google developer recommender systems tutorial. You'll find a nice tutorial on how to implement it. Okay, so now what's the problem? Yeah, like I mentioned, the strength of the model is that it learns the importance of the topics or the categories as specified by the publisher of the item. When I say those topics, I mean the ones the publisher sent, not the embeddings which we were calling as categories. I mean ones inserted by the publisher. It learns the importance of those topics. It also learns the importance of the publisher in recommending items. The problems are, like we discussed, it learns that Lady Gaga video will be much more popular than a new video, and so it learns the importance of the publisher. Hence, it will keep recommending content from top publishers. It will lack of diversity. The model, as defined, learns a user embedding, a single user embedding. And what will happen is you'll find a lot of similarity in the items recommended by this method. There are ways to counter that as it is as I've drawn it here, it finds very similar items. Okay, next question is by Hussein. Why the two-step process, latent embedding and then embeddings with categories? Why can't this be done in one step? Latent embedding and then embedding with categories. So to explain this again, this is actually this rectangle item embeddings. This is the output. It's not process. This is the output. Once, what is this output of? This output of this arrow is actually a neural network. This is think of it as a function, and a converter, an encoder, if you will, which takes three things. One is what categories are specified by the publisher, the identity of the publisher, and third is this random vector which we have trained, and after training means something to the model. It's to capture what is not explained by these two. So this function takes all these three and produces a single output. This is not what we are now calling the item embed. Okay, thanks. So the problems are rich get richer and lack of diversity. So there's a very nice paper, Maximal Marginal Relevance. It's about 21 years old. What that paper does, and I mentioned because this is the exact same approach that we use even in high frequency trading. But when you have a set of items and a ranked list of items, and you don't want the same ones at the top, what you can do is select the top one, select the one which is the highest score, and then penalize every other similar item, like penalize a little bit, deduct their scores a little bit, and then see which is the next highest. So in this case, what will happen is, before doing any diversity boosting, let's assume that this was the rank list, item 1 from A, item 2 from A, item 3 from A. So you selected item 1. And then you reduce the scores of every other category A item. Then you selected the second item and you found that, since our category A items score has been reduced, now the second highest score is one of category B. Similarly, so essentially the idea is that once you select an item, you have some penalty to items that are very similar. So let's also give some names to it. Let's say category is sports, and B is news, and C is technology or something. So you don't just show sports to the user. After sports, you show news, and then technology. And then you can build different user experiences. Some could say that, hey, this is a lot of cognitive load. Can you make it easy for me? So one could and group it into ones from different category, and then sort the categories based on the score for the user. I want to go. The reason I'm going into this in detail is because these are the user stories that we that we get from UXR, and following these yielded significant improvements when we actually implemented them at work in Google. It's led to almost doubled the engagement metrics. So if you listen to your users, they will often tell you what to do. The model that we used here was very simple 20-year-old model, but it was very impactful. Now, so far I've just been talking about category, and just a simplification. Another way to do diversity boosting is by user story. For example, you might be interested in fresh content. You might also be interested in content that is the top content, like top content over a long time. You might be interested in niche content that is getting unusually high likes. So you can these need not be different categories. These can be different reasons. These can be different flows of picking items, different user stories, and you can diversify across them. Okay, Vivek is asking, can you briefly explain how this was used in high-frequency trading? The reference I made was, in high-frequency trading, you have typically you come in to trade and you have, let's say, 20,000 strategies to pick from, but you wouldn't pick 10 or 20 to trade that day. How do you choose which 10? So what you'll have is, for each of these 20,000 strategies, you will have a back test. You will see their historical performance on simulated data, and then you will sort based on that, and you'll get a rank for each strategy. So this is a strategy with the highest back test, this is second highest, third highest, etc. One solution is you pick the top 10 and you trade with them. The problem is that they could all have a very similar loss, like a market lose money could be similar. Hence, diversity boosting helps a lot, where you pick the top one, then you add a penalty to every other strategy that is very similar to that one. And then you pick the second one and repeat the process. Can we apply, Ravi asks, can we apply explainability like Shapley values in a two-tower approach to find the top embeddings as a reason for the recommendation? So explainability has not really, I mean, it seems there are, if you look at the approach, it feels like one should be able to explain things like, hey, I'm recommending this Peppa Pig video to you because you have watched that other Peppa Pig video. And that is much easier to do in a seed-based recommender system. I'll explain what is seed-based, but in a different way of recommender system. In a two-tower model, where your user embedding is meandering through many examples, explainability, there's a very nice paper on it, but it's not something that is being used in production. It is just a little hard. And I haven't seen practical success stories of it. Please reach out to me later. I can point you to the paper by Mukund at Google on explainability in a two-tower system. Now, the seed-based recommender system, also very popular, is exactly that, hey, you watched a video and I know which other videos are very similar to it. I will only recommend those which are next to your seed. And in doing so, I will remember the reason why I'm recommending it to you. So if you make explainability a goal of your recommender system, you're probably better off starting with the seed-based recommender. Thanks. Okay. Okay. So the second problem was rich get richer. So what are we going to do? We are just going to remove that data source from our item embedding encoder. So this arrow is working off inputs, and we're just going to remove that publish. So in the context of TikTok, the claim is that every creator has an equal chance of being viral, right? Equal chance. Only way you can have that is by actually not having the identity of the creator as an input to your recommender. But what is the problem with that? Firstly, it's jarring because, if you ask person, do you think a video by a popular publisher and a new one, are their expected likes the same, or expected watches, expected quality the same? They would say no. It doesn't make sense. But also in terms of quality, what will end up happening is you're suddenly increasing the set of videos that you consider good by a lot. See, the only input you have left is the category. You might have millions of videos with that same category. How do you know which is better? Okay, but users still have a preference for the creator publisher, right? Can't we just do explorations instead? Manu asks. Exactly. Users have a preference for a creator, but we are forcing ourselves to remove that from the model. If we have removed that, then the embedding learned is purely a function of the category. We are purely learning that this user likes, I don't know, funny videos with a cat in it. And if I make that funny video with a cat, or you make that, or I don't know, a good publisher on TikTok makes that, the embedding will have to be the same. So we have now made our problem much harder. We now have to figure out among these millions of videos which ones users will like. The solution, like if you think about it, like if I were to manually ask you to do this, there's only one solution you will do. In the sense, you will try and see. You will try every one of these possibilities a little bit, performing better than average, and then try it more, and slowly, like it's a massively parallel experiment along all of these million videos that they have to do, because they are not letting themselves use the prior data of the publisher. Okay. So this experimentation is also called stochastic ranking, because it includes an uncertainty in it. When an item is initially added to the platform, the uncertainty of the performance of the item is high. It could be good, but chances are it's not going to be liked by many users. The way we do that is we use that estimated click-through rate, plus we add a big noise to it because we don't know about it. Another way to think about it is that, let's say these red lines, red dotted lines, is our current estimate of each of these videos. Let's say we have 5 videos, D1, D2, D3, D4, D5. And based on this these estimates, the red lines, we should be recommending D5. But let's say D4 is a newer item and there's much more uncertainty. We have a much wider range of how good that video is. Essentially, what is the expected click-through rate? So based on that, the upper confidence bound of D4 is higher than D5. So in this case, we should be recommending D4. In fact, you can do a little more than that. Instead of upper confidence bound, you can do Thompson sampling, and there's a probabilistic model. But essentially, for new videos, you give it a shot and you see. And once you have given it a shot, your uncertainty goes down. You either know it's good or not, a little bit. So this is this massive parallel experiment that is going on in a platform, and it only works when you have users to experiment with. You cannot have 10 users and run a massive parallel experiment. So it's a kind of a chicken and egg problem with the platform. That's it. I think what we talked about is, just to go back, we talked there are 2 problems: rich get richer and lack of diversity. And diversity we solved using this method, and then we talked about using to not have rich get richer problems. We're going to remove the publisher, and then we'll run a massive parallel experiment to see. Let's try videos and see how they are working. Questions talking about TikTok. Just another question, doubt I had. Might not be highly relevant, and you can choose not to answer. If you wanted to also take into account the real-time user behavior on the website, like products they're spending more time on, TikTok uses the time. Sure. Yeah, there are a lot of signals, and you're right. I mean, in practice, it's not just whether the user clicked on the video or not, how much time they listened to a video, what terms they have used in their search, TikTok search, but if you were to go to YouTube or something, yeah, the search queries, you can use a lot of other signals. Sounds good. Any, yeah, let me know if any other questions also.
Our open house for questions now, folks. Let me take some more questions, and I'm also sharing a feedback form here.
Can you elaborate a bit more on the stochastic and deterministic part? Okay. Yeah. So actually, it's about fairness, and I think someone was talking about explainability. It's a related concept. So if you're building a recommender system, if you have deterministic ranking, which means your model came up with some scores, and you ranked based on that, and you showed users the platform. You know what? Let me scroll back. Okay. Okay. You ranked and you scored based on that, and so what will happen is every time you'll be in this small set of videos or content that you'll keep recommending to, and you will not experiment with new items. That is because you don't have, I mean, for each new item you have only a little bit of information. You want to in reinforcement learning terminology, you want to explore and not just exploit. Stochastic ranking, what it does is it says this is the mean estimate of the goodness of the item, but there is some uncertainty as well. So I'm going to take a probabilistic value of I'm going to sample from that range where the expected click-through rate is, and based on my samples, I'm going to rank. And it could be that, hey, there's a new video published by somebody who's never been on TikTok, and hence the uncertainty is quite wide. And hence I 1 out of 1,000,000 times when I sample, the sampled value is quite, I get a high CTR, and hence it is ranked high for 1 out of 1,000,000 users. But once that is shown to the user, maybe that user likes it. And now we have a better estimate. The uncertainty goes down. We'll show it to a few more. And maybe by the 100th user, again, the click-through rate goes down and we start showing. So that's how stochastic ranking works. John asked, what was the name of the paper that you mentioned 21 years ago? It's Maximal Marginal Relevance. It's by James Carbonell. Maximal Marginal Relevance. Ramesh asks, do you think about personalization for transactional products, furniture e-commerce, differently than habit-forming products? Yeah, I think the good question. The closest product platform I have visibility is in shopping and Google Shopping, and the models are the same. Again, the same two-tower models and stuff. However, what we are trying to learn about the user is the journey that they are going through. Like, for instance, what is the meta action that they are doing? You give good examples about furniture. So buying furniture, are they going through this journey of, I don't know, home decoration or something? No, it's not just every item is different. We try to connect them into journeys which last a certain time, and there's a long-term preference of the user. Okay. Cool. Thank you. I think that's about it. Share my email. Yeah, feel free to email me or ask me questions on LinkedIn.